So does everyone get the slide for this class? Okay. So let's continue on the modeling for a generator. On Tuesday, we derived the power transformation, and then we change the flux and voltage equation from the original reference frame about phases A, B, and C. So we transfer to the new frame about 0, D, and Q. So we have the new flux linkage equations and new voltage equation. So now in those two equations for each matrix, every value will be constant. So which will be the good model for simulation and for study. We also explain the meaning of the input in this voltage equation, which is the last column on the right-hand side. So this one has two non-zero elements. So each element is proportional to the speed of the rotor, and also indicate the coupling between the DSs and QSs. For instance, the input in the DSs circuit is proportional to the flux linkage in the QSs, and the input in the QS is proportional to the DSs. So this item, if we treat the two input as the two components in the DSs and QSs, this one actually represents a vector revolving together, actually proportional to the speed. So because this can be concluded from the Faraday's law, because generator deliver the electricity to the terminal, to the load, through both electric field and also magnetic field. So the first item is means the electric energy delivered from the field winding, from the field circuit by the DC source and to the terminal. This part of energy is very small, but the majority of energy is delivered through the second item, proportional to the speed. So this makes the generator be different from a transformer. So if we have a generator connected to the system but without any speed, so it will not behave as a source. So it will not deliver large generation to the grid. It will operate like a transformer. Okay, so let's continue. So far we proved we can utilize the transformation. We call it power transformation to transform the instantaneous currents in the phase A, phase B, phase C into a new frame, and we call it ID, IQ, I0. Okay, so there's three coefficients, K coefficients, as long as they take a constant value. So the transform currents will be always constant. So by constant, this means, so if the frequency is around the synchronous frequency, and also the three-phase currents are balanced, so those three currents will be a direct current. Okay, although here is still time function, that is because we assume the speed of the theta may not be exactly the same as synchronous speed, but under steady state balance condition, so those atoms will be constant. And we also indicate, so if we take those values for KD, KQ, and K0, this transformation will be power invariant. So you can utilize IA, IB, IC to calculate power, instantaneous power for each phase, and you calculate the sum, so give you the total power delivered to the load from the generator, or you can do all the calculation in this new frame. The power is exactly the same. It doesn't change the value. So that can be a very important condition, okay? But we really don't like that factor of the root of 2 or root of 3. That make a calculation be a little bit more complex. So is there any alternative transformation which is easier than this transformation, but we still can get benefit, we still can utilize the transform value for calculation of power? So let's see if we want to just make ID, IQ to have the seamless expression, right? It's pretty natural to have KD be equal to 2/3 to cancel this factor, right? To make KQ to be equal also 2/3 to cancel this factor. So K0, just make it be more meaningful. We can just let I0 means average value of IA, IB, IC. So K0 can be 1/3. So that will be the this alternative new transformation. So we just let KD equal KQ and equal 2/3, and K0 be 1/3. So we will have ID in almost same form as IA and IB. So we can have a unit to unit relationship, which means you get rid of this factor, right? So and KD is cancel this factor. So the ID will have a magnitude same as IA and IB or IC. So it's IM and with some sinusoidal waveform or function. So which means we'll have this ID and IQ in the seamless form, seamless expression. So for this case, the path transformation, we call it P tilde because it's different from original P. So you see, we don't see those square root of 302, right? So here, P and P inverse will be much simpler. So in many textbooks, actually, this is widely utilized, the path transformation instead of that one for power invariance. But you may wonder, okay, so now we don't meet that power invariance condition. So that means we're going to calculate some wrong power. We have to scale up or down using the calculation in the 0DQ. So we'll have that one addressed later by another approach. Okay, but now let's just take a look at this new transformation. So because P tilde is not the power invariant, which means the matrix is not orthogonal matrix. So if we calculate the three-phase instantaneous power in the original frame, that basically the summation of the three instantaneous power, so which is equal to the inner product of the voltage vector and the current vector. So we just transform the V and I to the new frame. So this item will not be one, not be I, not be identity. So we cannot get rid of this item. So if we plug in those P tilde and P inverse of P tilde, we'll have this expression. Okay. So which is like a weighted sum of the instantaneous power of three phases. So this one is different from the inner product of the vector in the new frame. So if you use that alternative transformation, you have to utilize this one to calculate the instantaneous power. Do you know why? Do you know why this one has to be weighted some? So there will be different weight on the instantaneous power in each phase. Why do they not have the same weights? Right, but why is only taking those K value, those weights will be one, but taking other value, they'll not be one. But definitely you can say it's because it's not power invariant anymore, but just think about why. So don't consider this one like mathematical equation, just utilize your knowledge from a power system. So if we consider a steady state balance condition, so when we calculate the power using the quantities from a frame A, B, and C, so each phase is delivering the power, right? Okay. For instance, current will have magnitude IM, right? But if yeah, so now when we transform here, we make I0 be the neutral current, which is 0 for most of time. So we only have two currents, right? So you scale down the magnitude, you have to scale up here to give you the same energy. That's why. Okay. All right, so if we take this similar transformation, this will be the new flux linkage equation, but this matrix is not symmetric anymore because the three hubs appear only on those three off-diagonal elements, but not on the other three. But there's one way we can get rid of those three hubs. We can introduce a per unit system. So for instance, this is actual value, right, in whatever the unit of indulgence. So if we can define a base value for this element, for this 3.5 mF to be 50% more than this item, right? So we will generate the same per unit value, but not the same physical units, but they can have the same per unit value. So we can eliminate this asymmetry by introducing the base value and per unit value. So we will still get the same indulgence matrix as the original power transformation. But someone even think this is still too complex because how many constants do we have? We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So we have 10 constant values. So if we don't introduce this per unit system, we'll have even more. So those three are different. So we'll add another 3 constant. Can we further reduce the number of the parameter here? Since we already introduced per unit system. So we introduce per unit system to get rid of the asymmetry between this element and that element. Can we by carefully designing the per unit system and base value, we make maybe those all the same? It's possible. So you may not be able to make every M or L to have the exactly same per unit value, but you can make maybe a maximum number of M or L having the same value. Okay, so that's called this per unit system. So we can make any self or mutual indulgence in DSs to be same, if that involve a stator winding. Okay, for instance, this one is a self indulgence in DSs for the stator winding, right? And this one involves stator winding and in DSs. So this one, we know this one may have some a little part related to the leakage flux. And this part really is the majority of indulgence not depending on the leakage. So this one is like a coupling or mutual indulgence. So we call it LAD. And in the same frame, so this one we can also make it be LAD. So this LAD, the second LAD in the second line came from the MF. By defining the base value of this one, we can make the per unit value to be LAD. Similarly, MD is actually the mutual indulgence coupling the stator winding and rotor winding, rotor damping winding in DSC. So that one we can also make that one be LAD. Okay, so similarly in the QSs, so this part, the mutual part is called LAQ because it's LL plus LAQ. And the capital MQ is actually the mutual indulgence coupling the stator winding in QSs and also damper winding with rotor in the QSs. So that one we can make it be LAQ. So finally, how many, if we can make this one happen, how many constant parameter we have right now? We further get rid of those one, right? So we have how many constant value now? 1, 2, 3, 4, 5, 6, 7, 8. Right? Right? Let me see. Yeah, we further reduce the number of constant. So this transformation or this handling to make sure the the mutual inductance, any mutual inductance involving a stator winding in DSA to be always LAD. In QS is to be always LAQ. This handling is called LAD, LAQ based per unit system. So all per unit mutual inductances between stator and rotor winding equal LAD or LAQ in DSs and QSs respectively, where so LAD basically just the mutual part in LAD. LAQ is just mutual part in LQ. Question? Any question? Yeah.
Stand for armature?
Yeah. So if you, I guess if you read the Quinter's book, it just find the first equation. It start using the LED. A means armature. Yeah. Armature in D. The L means leakage. 0 means zero sequence. AQ is armature in QSs. Yeah. Okay, so this can further reduce the number of constant model parameter without sacrificing any accuracy. So those transformations, if you define the base quantity properly, everything is accurate. We didn't approximate anything, okay? But we have reduced the number of parameters significantly to this one. Okay, now we need to go over the per unit representation of per unit system quickly. So I believe everyone already familiar with per unit system. So why do we need to define a per unit system? Okay, or utilize per unit representation? Because any power system is operated at many different voltages by sections. So it's not convenient to use their actual unit in like volt or kilovolt or ampere or milliampere. So it's better we define the base quantities for each section, such as we can only use like a number without any unit, which is like percentage of base quantity. So if we study only steady state behavior, typically we only just need how many quantity do we need? Like if you took the 421 parts, how many base quantity do we need? How many base quantities do we need to calculate? Only need 2.
We have 2. We can calculate the rest.
Okay. Yeah, if you know any 2, which means we consider the voltage, current, impedance, and power, right? So if you know any 2, the other 2 will be calculated. But when we study dynamic, we have to add another one, which is frequency, because frequency may not be exactly 60 Hertz. So we'll have a totally 5, but not all the 5 are independent. So you have to introduce, for the first 4, you have to introduce 2. And the last one, you have to maybe add another one. So it'll be 3 independent. Only 3 of them are independent if we consider frequency. Okay, so if we consider a generator on the stator side, so which means that the stator is connected to the power system. So the generator has to be operated at certain voltage, right? We can use that voltage as the base value. And here we use peak value, peak voltage of rated line to neutral voltage at the base voltage of the generator. And we use peak value of the rated line current at the base value. And if the rated frequency like 60 Hertz or 50 Hertz will be the base frequency. So those 3 will be minimal bases we need to calculate the per unit value. So we can utilize the voltage and the current bases to calculate the power base. So here we use a 3-phase power base. So to calculate the 3-phase power base, it will be 3 times the power, the RMS value of voltage, and RMS value of current, right? RMS value is equal to the peak value divided by √2. So here we'll have the factor which is 3½ of the product of the peak value of instantaneous voltage and current. So next, for the rotor speed, so we can also define a base. So if we already know the frequency base, multiplied by 2π will be a omega base, will be a rotor speed. So the unit is radian per second. So we use this one as the electric speed, but if you want to really find out the mechanical speed, so you need to, so mechanical speed multiplied by the number of pairs of poles will be equal to electric speed, which means if you have 2 poles, so this one will be 1. The mechanical speed is same as electric speed. You have 4 poles, the mechanical speed will be half of the electric speed. But the more poles, the lower speed you can operate the generator to give you still 60 hertz. Okay. So remember this number, this basically means radian per second for 60 hertz, 377. So we also need to introduce a time base. Time base is not in the unit of second, it's in the unit of 1/omega base. So that unit is 0.0027 second. It's 1 unit for per unit time. So this can be convenient if we introduce some parameters later on the generator. So if we define time to be also per unit, not in second, that can make formulas much simpler. So impedance base in ohm will be equal to just E over I, right, by definition. So inductance base in Henry is defined to be the impedance base divided by omega. The flux linkage base by definition is equal to the product of the L and I for the base value. You can also utilize the voltage divided by the omega base. Torque base is defined to be power divided by not electric speed, but mechanical speed. So it will be calculated by this formula. Okay, so by introducing those base values, we can change all the quantities into per unit. So they will become a number. Don't worry about the unit. After you finish all the calculation and depend on which that quantity is, you can multiply that value by the base, you will get physical value. So here I have to mention, so when you calculate the base for reactance, which means the actual reactance divided by impedance base. Okay, so actual reactance is actually the electric speed multiplied by the inductance by definition. And impedance base is equal to the omega base multiplied by the L base. So you can see if F is equal to the F base, which means the current frequency is almost exactly same as 60 hertz. So that makes per unit reactance be same as per unit inductance. So that's why in some manuals of the generator models, they like to use L everywhere in per unit, which means X. Okay. So for reactance, some like to use always X, some like to use always L, but in per unit, they are really same. But if the frequency is equal to 60 hertz, if frequency is not equal to 60 hertz, that can make they have a slightly difference. But in reality, most of power system, if it's operating, the frequency should be very close to 60 hertz. How close? Like typically less than 1%, right? So even you consider that 1% difference, so those values can still be very close. All right, so next we have to define the base quantity for each circuit. So how many circuits do we have? We have a circuit in DQ0 and also with field winding circuit and the damper winding and in D and Q. So we have six individual circuit for the cylindrical rotor generator. For round rotor generator, we also need to add another column. So each circuit need to have like individual base quantities. Okay, so for stator windings, they can share the same base quantity because they are actually connected, although they operate in the same voltage or current level. But for the rotor windings, they are isolated from each other. There's no electric connection between any of those rotor windings with the stator circuit. So field winding is operate on its own, and damper winding, it can be just the squirrel cage embedded into the rotor, right? Not connected to any other circuit. So we don't know what voltage is really operating, okay? But we do know if the rotor revolving, they all operate at the same frequency. So they can share the same frequency base, F base. But they definitely have different power base. So we just assume they have three different power base. And we don't know their voltages, and we don't have to. We can define their power base. Okay. So the conclusion is to choose the base quantities for all the circuit. So we first determine the base quantity for the stator windings, and for rotor winding, we utilize the stator winding power base as a power base for rotor winding. And then we pick those current. So we can select the IF base, ID base, IQ base to make sure, together with the power base of stator, to make sure finally we'll have symmetric per unit inductance matrix in the LAD, LAQ per unit system. So that's here how we can, the condition to determine those three bases. So we need to achieve this the most simplified inductance matrix in this slide. So this is our target. Okay, so we need to select ID, IF, IQ bases to make sure the per unit will have this simple form. Okay, let's talk about how do we generate this LAD, LAQ per unit system, starting from the original flux linkage equation. The first step, we need to make this matrix to be symmetric. Okay, so assume we have a base quantity for each one, and in the per unit we'll have so we have this IMF bar and IMF bar prime. So this one may not be same as MF, but if we select the base quantity properly, we can make that the right MF be equal to the blue IMF prime. So how can we do that? We just use this one as one example, but you can do similar things for the others to make the matrix be symmetric. So let's pick this first equation, the equation about the psi d. We use that one as an example. So we pick the first raw equation, and we divide the both sides by a psi s base. Okay, the stator flux linkage base, which is equal to the inductance base, stator inductance base, and multiplied by current base. So the numerator is actually the first raw, right? This is the first raw equation. And both sides we divide, it's divided by the flux linkage base. Left-hand side is just psi s base. Right-hand side, each item will be same. Okay, next one. Because we're going to change, we're going to divide this IF. This is not the IF, so we have to divide this IF by its base. So we assume there's a IF base. So IF divided by IF base, it will give you per unit current for this field winding. So because we divide this one by IF base, we have to multiply this item by IF base. So then this one will become IF per unit. And this one can be something like MF per unit. So this is exactly MF per unit. Because this one, the first item changed to a LID per unit, right? The last item, similarly, the last item will be the MD per unit multiplied by ID per unit. Is this clear? So this whole bunch will be the MFIF divided by the LS, the IS base will be the MF per unit. And the MDID divided by LS and IS will be the MD per unit. So second, we'll try to find this one. So by the first line, we know how to find the base value, how to find the per unit value for the MF, right, from the first row. And MF also is presented in the number 4 row, right, related to the psi. We also use the fourth equation to find out this per unit value. So that value should be equal to that value. So then the second step, we divide both sides of equation psi f by psi f equal to LF and IF base. So this 3/2 is here. So each item is divided by the product of IF and IF base. So from this step to that step, we divide each current. If it's not IF, we divide by its real base. So because ID is divided by IS base, so this part should be multiplied by IS base to make sure this item is equal to that item. So similar, last term we have ID, so need to be divided by ID base. So the numerator need to be multiplied by ID base. Okay, so that means this item is actually the MF per unit. But we call it MF prime because this one can be different from MF. But if we make MF prime to be equal to MF, so we just let this item be equal to that item. So we can get a relationship to know how can we determine the F base, such as the MF is symmetric in the new matrix. So that come to this third step. So those two has to be equal, which means this one is the MF base, this one is MF prime base. So there's like factor of 3/2, right? Those two have to be equal. And this MF is equal to that MF. Those two are same. Those two will be canceled. Okay, then we just simplify this one. Become LF multiplied by IF square is equal to 3/2 of ILS multiplied by IS square. So if both sides we multiply by the rotor speed base, so left-hand side is really just because omega L multiplied by current is become the voltage. So left-hand side is actually the voltage base multiplied by current base in the field winding. The right-hand side is 3/2 of the voltage multiplied by current in the stator winding. So this part is simply just three-phase base. So what this equation tells, the power base in the field winding has to be equal to the three-phase power base of stator winding. So if we make this one hold, that matrix will be symmetric for MF and MF prime locations. Similarly, we can have the other two equations. So for each rotor winding, its power base has to be exactly the same as the three-phase stator power base. So if those three equations hold, we will have this matrix to be completely symmetric in per unit value. So this explains why in the previous slide, so we show the table. We usually assume the three rotor winding have the same power base as the stator. Okay, so this assumption make sure the inductance matrix to be symmetric, but it doesn't ensure the per unit value are same as the LAD, LAQ. We still need to choose those three values properly to further make all the mutual inductance in DOQ to be LAD or LAQ. So that will be the next step. Okay, so next step, we want to find the base value such as we have only LAD and LAQ for the mutual inductances involving the stator winding. So how do we do that? We simply just assume like MF, this MF is equal to MD, okay? And which is also equal to this LD if we don't consider the leakage part, the mutual part. So LAD is actually the difference between the LD and the leakage inductance. So this one will be equal to the MF and the MD. Okay, so we take those two expressions from the previous slide. So those two has to be equal. So immediately we get, so IF base has to be equal to LAD. LAD is measured from here. Okay, so LL is leakage inductance, you can estimate. LD is a self-inductance, you can do some test or measure. So the difference is LAD. LAD is the leakage doesn't, it's not lost due to the leakage. Okay, it's contributing to coupling the stator winding. So that's called LAD. So LAD can be estimated. So you use estimated LAD, and also for the mutual inductance, you assume you have certain way to estimate the MF, and multiply by the stator current base. So this one will give you the field winding power base. So this one is power base. And starting for the field winding, all the other items you just utilize the same current base of field winding. Similarly, you can for the damper winding DICs, assume you can measure the mutual inductance in D, and you already know the LAD. So LD base should be calculated by the first equation, Green equation. Then the following formula just calculate the other bases. So for the Q axis damper winding, since we only just have one, that one need to be equal to the LAQ. So we have this set of formula. So after doing those steps, we'll be able to get a new inductance matrix for any off-diagonal element that involve a stator winding. That one has to be either LAD or LAQ. And for the diagonal element with stator winding, for the mutual part, that has to be either LAD or LAQ. So this is so far the simplest inductance matrix we have. Any question? No. Per unit value of MF is just LAD.
Base divided by L as base.
So this is a derivation. This derivation just tell you if you make a per unit value in the field winding and damper winding to be same as LAD, so this one has to hold. Then the conclusion is you have to determine the IF base based on this one. So this is taken from here.
And all that's equation from last page y MF per unit value is equal to MF times R base divided by L as base. What this equation came from?
this is at MF per unit, right? Let's start. So you don't understand from this step to this step, or from this step to that step. Okay. The first step, it basically you take all the numerator items, they come from the first equation. And on both sides, you divide the both sides by the psi s base. Because left-hand side, you have thought linkage, basically just psi s base. Right-hand side is product of ls and s, you just multiply, divide each item by this one, right? And the next one, you want to change each current to per unit value. To do that, you need to divide that current by the base value. But this IF, you don't have IF base. So you have to assume there's IF base. By dividing IF by the base, you have to multiply also the base to make this second item the same as the second item in the first equation, right? So this is that clear from this step to this step? So from this step, you know this part will be the definition of MFA per unit. No. Okay, so this is the original equation, right? This is per unit equation. The per unit equation compared to original equation only add a bar on top of each one. So if you change this IF to the IF per unit, so whatever multiplying the IF has to be MF per unit. Is that clear? Okay. Does anyone have question on this slide? Yeah. So this handling about ID is similar to this one, right? So the thinking of this part is first you have the numerator part, the original equation. Then you write down this equation. You just simply add a bar on top of each one. Okay, so then you take a look at this ID already divided by the base. So this IS is exactly stated. So is that one you get this ID bar. But IF bar, in order to get IF bar, you need to divide IF by IF base. But the original equation doesn't give you IF base. You need to divide that one by IF base and multiply by IF base. So to make the equation be the same. So that increase the complexity of the first item. So that first item, you can put whatever into this IF bar. So that would be definition of a per unit MF. And this one will be per unit MD. Okay, so by finishing these slides, to meet those equations, those power base to be same for every one thing, you can ensure the symmetry of that inductance matrix. But it doesn't make sure all the mutual inductance in D and Q to be LED LQ. So next step, you need to make those two to be equal. Not just equal, they're also equal to the mutual part of LD. All right, is that clear? So there are two steps. So this step to make a symmetric inductance matrix. So next step to make the simplified inductance matrix. So here is only I only just put two slides. So that's based on my experience of teaching this part. This part is very, very painful to teach it. So first couple of years, only cover those two slides. I have to take the entire 1 hour lecture to work on the whiteboard, step by step. I still highly recommend everyone read Quinter's book. There are several pages describing how this one is proved. Then I figure out, okay, I maybe can use this slide. I may not make everyone understand 100% in this maybe 10 to 15 minutes, but it's very clear. You just use those two slides as reference to read through those pages on the Quinter's book. I believe in reality you only have maybe you only have any chance to really calculate those base value per unit value. But this one just tell you it's doable, right? All the following equivalent circuit and model are based on this one, not based on that one. So there are already somebody else working figure out those base value for you. Okay, they give you per unit matrix and per unit model. And it is safe to use for any stability study. You don't have to do it on your own. Somebody already did that for you. Okay. Okay, let's summarize. So we start from this very beginning model. We use this voltage equation as one example. So even we assume we know the resistance of all windings, and we even assume the three armature windings have exactly the same resistance. So that largely simplifies the first matrix about the resistance. But this one will be really painful matrix. They have so many inductances, and most of them are theta dependent. So if we consider they're symmetric, okay, so there's only 6 constant inductance all on the right bottom corner. But most of other, like there are 15 theta dependent inductances. So this is definitely not good model to use. So then we introduce path transformation. By introducing path transformation, we get rid of the theta independence. So make everything to be theta independent. We get rid of the theta dependency. So everything here will be theta independent. So it's safe to pass all the perimeter. If you can, you have the generator operating in certain environment to do the testing, which can be done by the manufacturer. They can pass those perimeter to you. Okay, you can do study. Don't worry if you connect the generator in a different environment, and because theta is changing, those value will change. No, they will be constant. So this is first good model. But you still have 14 perimeters. Every one is in their original units, physical unit. So next we introduce this idea of a LED, LEQ based per unit system. So now we only end up with 8 constant values. So this is good. It's a very simply, it's a well simplified model. And all the mutual inductance in D will be LED. Everything in Q will be LEQ. Okay. So when we make all the mutual inductances in DIC to be LED, that introduces a large benefit, because next step we're going to redevelop the equivalent circuit. So early we have the equivalent circuit. We have on the rotor winding we have 3 isolated winding, like a transformer. Then we introduce the path transformation to change the stator winding to be in the 0 DQ, but we still have like transformer circuit. They are isolated. But now we want to introduce an even simpler circuit, and by making those mutual inductances to be same, that largely simplify our circuit. Right? Because if we develop the equivalent circuit based on the second equation, MF, MD, they need to be represented by different inductance. That's it in the circuit. But right now, they actually share the same branch. So only need to have a single LED in the circuit. We don't need to have different MF or MD. So this one can further simplify the circuit. Okay, let's work on the equivalent circuits. So the first equation is a voltage equation, and second is a flux linkage equation. But compared to the previous version of flux linkage equation, multiply both psi vector and current vector I vector by P. A P here is just a differential operator. It just means derivative of psi and derivative of current. Why do I do that? Because we're going to create equivalent circuit. It's more convenient. We only consider current, voltage, and impedance. And flux linkage, the derivative of flux linkage will be the voltage. So we can match any like P psi item into maybe the voltage drop in the circuit. So that will be more convenient. Another thing we can conclude is if we compare this row of each row in the right-hand side of flat linkage equation to the second item of the voltage equation, they're actually identical. So this part is exactly same as that part. Okay, so which means you can plug in the right-hand side of the second equation into the second item of the right-hand side of first equation. So immediately you get those equations. There's no simplification. Basically just exactly is exact equation. Okay. You can get rid of those indulgence current and you only have this part. This is also helpful. So we have those three set of equation in front of us, so we can start to derive the equivalent circuit in each axis. Is that clear? Right. Okay. So we pick the first equation in the D axis, which is basically the second row of the first equation, right? ED is equal to RA multiplied by negative ID, which is the last item. Then we have LL plus LAD multiplied by negative ID, which become the first item here. And this LAD multiplied by the IF will be this item. Then we have, what else? Yeah, we have this LAD multiplied by ID will be this item. And also we have the input, negative omega R and sec Q, which will be here. So this is exactly just a second equation. Okay, next. If you look at this equation and based on what I said, so we want to find a circuit which is very simple. We don't want to have many components having the exactly same value, right? So if there's any component which have indulgence of LAD, we only have just one component. We don't want to see 3, 4, or 5 different components. But this equation, if you want to realize or maybe make this one make a real circuit based on this equation, the simplest way is you assume the voltage drop is caused by indulgence due to this current, and another indulgence due to that current, and this indulgence due to this current, and then input and also resistance. So in order to realize this equation, how many branch do you have? 1, 2, 3, 4, and plus input. And also those 1, 2, 3, 4 branches, they all have different currents. So how are you going to realize that one? It's very hard. But let's see, maybe we can, let's assume this LED, that LED, and that LED is exactly the same branch. Okay, so we just merge those three together. They together carry 3 currents. So that's the idea. So we want to minimize the use of branches in the circuit. So this equation is the second equation, voltage equation in the D axis, which come from the field winding. Okay, and this is the damper winding equation, and this is the EQ, the Q winding, stator winding in the Q axis, and damper winding in the Q axis. And this is the first, this is flux leakage equation in the D axis for stator winding. And this is the flux leakage equation in the Q axis. Okay, so those are the equations we have. So first, let's assume there's only just one LED, so which will be some branch. Because this LED is multiplying the ID, F, and ID, I just assume this LED is carrying all the 3 currents. So I just move those 3 currents into this parenthesis. Okay, so this will become from those 3 items. So the remaining item will be here. So this one will be from this LL multiplied by ID, and this one from input, this one from resistance. So this is how we did for the first equation. So I make a different color, just indicate there could be two branches. The first branch has residence LED, and the total current is the sum of the three current components. And the second branch, I use the orange color that indicate maybe there's someone carrying the current of ID that share the same current. I use the orange color so to implement this equation, I can use this circuit. So it starts from ED. At first, I have voltage change due to this resistance and that current. So it will be RA carrying a current ID. And because it's a negative sign, the current is actually coming out from positive terminal. Okay, so the direction is ID is coming out from the positive terminal. And then there's another voltage drop due to the omega and the psi Q, so which will be here. And because the negative sign, so the negative sign will be in the direction of the positive terminal. So it will be opposite to the ED. Okay. And the next item is voltage drop due to the leakage residence. So there should be someone called LL, a carrying ID, and also opposite direction because of the negative sign. And the first item can be implemented by single branch that has inductance LED, but there will be three currents. Based on the sign, ID will be opposite, will be from bottom to top. The other two current IFID will be from top, will be top down. Okay, so this is how I implement the first equation by this circuit. But this, so it's good circuit, but we still have yet to explain where do ID IF come from. So that need to be explained by the second equation. So that's our target for second equation. Okay, so now we already have this branch and that branch. We need to keep those branches. So we need to create the right branch for this equation. So we just put this right branch here. But compared to this equation, because we add F and ID, so this one is LAD is only multiplied by ID. It's not multiplied by IF or ID. So if we put this right term at the first term, we need to get rid of the IF and ID. So there will be LAD multiplied by the sum of ID and IF. This will be a negative sign. So purpose of this second item just to cancel the IF and ID current component. And the other item, basically, we just moved on, okay? Okay, next one. So because there's a ID and the IF, okay, and this item has ID and this item has IF, we have to give this item a reason, right? Assume there's some branch carrying the total ID and IF, which is this one. So we need to create that current. And because IMR is related to ID, LF is related to IF. So it makes more sense. We just assume IMR also goes through ID and IF. So we make the second and third item to be this purple one, which has the current of ID plus IF, but the inductance is negative LAD from the second item and positive IMR from the third item. And we color this one by purple or magenta, whatever color, pink. Okay. And then the remaining parts I found out is only about IF. So I just color them in green. So we create three groups. The first group about current negative ID, IF, and ID, a capital D. The second group about current ID, IF. The third group about only IF. So we just further draw those branch, which will be this one. So this section, the purple section will be will explain where this ID and F come from. So total inductance will be MR minus LAD. And the last group we colored in green, that one only carry the current F, okay? So the voltage change is caused by first there's a source. And second, there's an inductance of the difference between F and MR. Okay. Okay, so further we do we have one equation left in the DSs because we already create those color branches. I just put those branches there, and I found out the difference only about ID. So ID will become the blue branch. So that explains where the current ID come from. So ID will be from this blue branch. Yeah, this can be very complex, but I quickly summarize the thinking behind those steps. The first, because many equations, they share the mutual inductance LAD. So to create this circuit, we assume only one LAD. So that is here. But LAD will, LAD item will be multiplied by 3 currents. So there will be a 3 current going through the LED. Okay, 1 current going to the stator and the other current, 2 current going to the rotor. And for the rotor side, we have to explain, we have to identify that current, and then we determine a branch which has the current ID and F. And then we push everything else on to the left, to the last part, which only come from one single current. Okay. So we can do similar thing for QSs. And we only have just one LAQ. So LAQ is LAQ has 2 current, a negative IQ and a positive I capital Q. Okay, let me see. All right. So where did I use those side of equation? So those equations to explain what happened on those voltage source. For instance, this EF. EF is equal to RF multiplied by F plus psi P psi F, which is this part. That helped to explain. So the flux linkage, the change of flux linkage due to the voltage, the field voltage, and also the voltage drop on the field winding resistance is equal to change on the flux linkage in the field winding. So another example is this last equation. This equation tells the voltage drop due to the resistance in the damper winding QS is opposite to the change on the flux linkage in QSs. So which is explained by this component. So this the voltage due to flux linkage change in the QIC damper winding is equal to the voltage drop on this component because the current is opposite direction. So not from positive to negative, it's from negative to positive. All right. So those 2 circuits is exactly present all the equations above. Okay. So there's no approximation. It's just one-to-one mapping from those 2 circuits to that set of equation. In other words, if you know those 2 circuits, you can redevelop every single equation above. Okay, so let's take a look at those 2 circuits. We use DIC circuit as one example. So this side is connected to the power system, the load of power system. So the DIC circuit represents the equivalent circuit of generator in the DICs. Okay. So it seems to be two sources inside of the generator. One is from the field winding, which is EF, and the other is this part, proportional to speed. As I explained, this part, the one proportional speed is actually the majority of the source of the generator, and this field winding is only just try to generate this magnetic field. So this one compared to the speed voltage or the one proportional speed can be ignored. And in the QSAs, you don't have source. You only have just single source, which come from the flux change and speed in the DSs. Any question? All right. So next, maybe we can further simplify the circuit. Why? Because this represents a single inductance, but it's equal to the MR minus LAD. MR is actually the mutual inductance in DSs of rotor. LAD is the mutual inductance involving a stator winding. So those two have different meaning, right? MR is completely in rotor. AD is in stator, but rotor stator is actually stay together. It's just inside of generator. So you may wonder, why do I keep the both? Okay, can I just simply call this one to be something, some L? Similarly, for this item is inductance. It's actually in series connection with the field voltage source and resistance, but it's different between LF and MR. What is LF? LF is a self-inductance of the field winding in rotor. And MR is the mutual inductance in DSs of rotor, right? So the difference will be this inductance. So we may be able to further simplify this one. So then we come to the conventional namings for all the parameters. So those highlighted one will be same as most of the manual of a generator model. And here we do some we rename some of the quantity. For instance, we can assume MR minus LAD to be 0. Although they're different, because MR is the mutual inductance only with rotor winding. MAD is the mutual inductance involving stator winding. But if the generator design are very compact and all the winding, no matter rotor and stator, if it's mutual, it's always about the same. It's all share the same set of flux linkage. We can assume those two to be very close. And that gave us a large benefit because adding this branch can make a circuit calculation. This inductance as LFD, it just stands for the field winding inductance. The field winding inductance is equal to LF minus MR. And field winding resistance is just equal to RF. Okay. And EFD, we just called E capital F as EFD. So by doing this, we come to this convention of the of most of the manual. Okay. Okay, what else? Similarly, in the QSs, we have so this circuit is different from previous slide because we add another branch. So here we assume this generator to be a round rotor generator. So the round rotor generator, we need to add a second damper winding. So you can tell. So we use a number to indicate which damper winding it is. So for ceiling pole rotor generator, we only have just L1D and L1Q, but for round rotor, we have L2D and L2Q. But those namings, just for example, to give you as example. So you're going to generate those equivalent circuit in the first homework. Any question on this? So I will. This is the last slide. There we go. I don't know how to get rid of. Okay. Yeah. So this one just explain how good this model is. So this is exactly the equivalent circuit, two equivalent circuit we developed, but different from the previous slides. You can tell. Okay, so this is the field winding, and this is stator winding. Yes, this is the damper winding, but it also adds another damper winding. So which means this circuit has a one stator winding, two damper winding, and one field winding in the DSs. And in the QSs, for the symmetry, they give you three damper winding. So first damper winding is same as what we derived, and the other two is you just simply add following the same structure. So this is the first very accurate model proposed many years ago. I think back to 1980s. So you can find this report. Report just discuss how accurate this model is compared to the field test. So you compare the response from the real generator measurements compared to simulation result of the model. So they match very well. Okay. So this is probably the most accurate model you can see in any of the stability study. So having three rotor winding in each axis, plus the stator one, you have 4 windings in each axis. You have 4 in the D axis and 4 in the Q axis. Okay, most of study only can need maybe 1 or 2 damper winding in each axis. That would be good enough. All right, this is my last slides for today. Okay, so next lecture we will utilize the model to do some calculation.